All right, today we're going to be talking about the Squeeze Theorem, also known as the Sandwich Theorem. You can use whichever name you prefer. But the Squeeze Theorem in mathematics deals with limits. It says that if the value of some function g of x is always less than or equal to the value of some other function f of x, which is in turn less than or equal to another function h of x, on some interval containing the point C, and the limit as x approaches C of g of x is equal to some value L, and the limit as x approaches that same point C of the function h of x is also equal to L, then we know that the limit as x approaches C of f of x is also going to be equal to L. And when you are talking about the Squeeze Theorem, if you've taken a calculus course before, you've probably seen this illustration. You'll have a y and an x-axis here, like so, and then you'll have three different colored graphs. Maybe we'll do one in blue here. Just be some function here. We'll say that this is g of x, and then we'll have another function, do it in green, which will be in between the other two functions. We'll say that this is f of x, and then we'll draw our last function, h of x here, which is going to be up top. Maybe it comes down at some point. H of x, and this point here, where they all come together, is going to be the point C that we're talking about. And intuitively, this should make sense. If we know that f of x is going to be squeezed between or sandwiched between the functions g of x and h of x on this interval, and we know that the limit as x approaches C of g of x is equal to L, which is the same for h of x, they both approach L as x approaches C, then we should logically understand that f of x is also going to approach L. I'm going to do another illustration here. I think this one is funny. I think it kind of looks like a sandwich. You might have to squint a little bit for that to be true. But I want to emphasize the point of this interval here. So for example, h of x could come something like this. This could be h of x, and then f of x could be greater than h of x over here, and it could come in like this. This could be f of x, and then we could do our little g of x here. Come in like this. This could be g of x, and we'll say that this is the point C. It's basically the same graph. But here, what we want to emphasize is that we're talking about intervals. So even though g of x is greater than both of the functions at this point, if we draw another point here, and the other point can end anywhere, it could be over here, and we say that this is A and B, then we can say on the interval on the interval from A to B, the value of g of x is less than or equal to f of x, which is less than or equal to h of x. And here you can see that even though g of x is greater than h of x at this point to the left of A, on this interval from A to B, the value of h of x is greater than f of x, which is greater than g of x. And you can see that here. So now that we've talked a little bit about what the Squeeze Theorem is, I'd like to go in and prove it. I will caution you, the proof for the Squeeze Theorem is a little bit boring, but don't worry, in the same video we're going to talk about some special trigonometric limits that are important to know that you can only prove using the Squeeze Theorem, and that's actually going to be pretty exciting. So the proof goes a little like this. If you know that the limit as x approaches C of g of x is equal to L, what does that tell us? Well, from the formal definition of a limit, that tells us that for any epsilon greater than 0, there is some number value delta greater than 0 such that the absolute value of f of x, or in this case we're dealing with g of x, absolute value of g of x minus L is less than epsilon, and the absolute value of x minus c is less than delta. And if you don't understand this definition, or if this doesn't make sense, I recommend going back and watching my video on limits, where I talk about what limits actually are, the formal definition of the limit, and I go through some proofs of limit properties and things like that. But basically what this is telling us is that if the absolute value of g of x minus L is less than epsilon, that's talking about g of x values that are within epsilon of L. And if you don't see why that's true, I recommend solving this inequality for g of x, and what you will get is L minus epsilon is less than g of x is less than L plus epsilon. And so basically what this is telling us is that g of x represents the range of y values that are within epsilon of L. And the same thing here, this is going to be c minus delta is less than x is less than c plus delta. So this is representing some range of x values that are within delta of c. And what this definition tells us is that no matter how small we try to make epsilon, meaning no matter how strict I want to restrict that domain around the y values, let's say that our proposed limit is 4, we can make epsilon 0.00001, and it would represent all the y values that are within that small amount of our proposed limit. There will always be some delta that will yield x values, which when plugged into g of x will give us y values in that domain. And if that's true for any value of epsilon, if there's always some associated delta value that will satisfy both of these inequalities, then we say that the limit exists. And so if we know that the limit exists for g of x, and we also know that the limit as x approaches the same value c of h of x is the same, it's L, then we know that this is true for g of x, and we also know that it's true for h of x. And I do want to point out that the delta values that will satisfy this limit for g of x might differ from those that satisfy the limit for h of x. Those two delta values might differ. So here I'm just going to add the condition that if delta is less than or equal to delta 1, this will be true. And here I'll say that if delta is less than or equal to delta 2, just so that we have some specificity within these two definitions. This delta over here might need to be something smaller than this one in order to make both of these inequalities true. So we'll say delta 1 for g of x and delta 2 for h of x. And looking at this is basically representing a range of x values within delta of c. That's exactly what it's representing. So graphically, if you think about that, it would look something like this. You could have 3 little areas here. One of those points is c, and then we could write c plus delta, and here we could put c minus delta, and that would represent the range of x values that exist on this line from c minus delta to c plus delta, as you can see here. And if we know from the Squeeze Theorem that we're dealing with an interval containing the point c, wherein g of x is less than or equal to f of x, which is less than or equal to h of x, kind of like how you see on this graph on this interval, you can see that h of x is less than or equal to, or is greater than or equal to f of x, which is greater than or equal to g of x. If we know that we're dealing with some interval where that is true, it's safe to say that there exists some other delta, we'll call it delta 3, where g of x is less than or equal to f of x, which is less than or equal to h of x. Taking all of this information together, what we know, if we say that delta is less than or equal to the minimum of these three delta values, delta 1, delta 2, and delta 3, then what we know is that L minus epsilon is going to be less than g of x. That's coming from this part right here. This is going, g of x, of course, is going to be less than or equal to f of x, which is going to be less than or equal to h of x, which is going to be less than L plus epsilon, which is coming from this part right here. And if we know all of this, then it's safe to say that if f of x is greater than or equal to g of x, which is greater than L minus epsilon, it's safe to say that L minus epsilon is less than f of x. And likewise on this end, it's safe to say that f of x is going to be less than L plus epsilon. And if you work backwards here, this tells us that f of x minus L is going to be less than epsilon and greater than negative epsilon. And what is this? This is exactly what we start with, the definition of a limit. This is the same thing. And so what we just showed is that if delta is less than or equal to the minimum of delta 1, delta 2, and delta 3, which we outlined above, then the absolute value of f of x minus L is less than epsilon, basically showing that we found some delta value, some relationship between delta and epsilon, such that no matter how small epsilon gets, delta will always be, or both of these inequalities will be true. Absolute value of f of x minus L will be less than epsilon, and the absolute value of x minus c will be less than delta. And therefore, the limit of f of x as x approaches c will also be equal to L. Alrighty, y'all. Now, as promised, we're going to move on to some actually interesting proofs. In order to do this, we're going to need to talk a little bit about unit circle anatomy. So if you're not familiar, this is the unit circle. We have the y and x-axis is here. And the unit circle is a circle with a center at the origin with a radius of 1. And so this point right here would be 1, 0, and the radius is 1 all around. And the unit circle has interesting attributes because if you talk about a triangle or an ordinary right triangle, you say that if this angle is theta, then sine of theta is opposite over hypotenuse. So the adjacent unit. These are the sides of the triangle. You have the opposite, the angle opposite of theta, the adjacent side, which is adjacent, and the hypotenuse is the longest side of the triangle. We say that sine of theta is equal to opposite over hypotenuse. Cosine of theta is equal to adjacent over hypotenuse, and tangent of theta is equal to opposite over adjacent. Those are the trigonometric functions that we talk about when we're dealing with triangles. And the reason that the unit circle is interesting is because the hypotenuse here is just equal to 1, because it's the radius of this circle. And so if we are to drop like a altitude here down from the point where the radius intersects, sine of this angle is going to be opposite over the hypotenuse. Well, anything over 1 is just itself. And so basically this distance here on the y-axis is equal to sine of theta. That's an ugly theta. And cosine of this theta is just adjacent over the hypotenuse, which is 1 here. And so this is just going to be cosine of theta is going to be this distance here. Maybe this would help if we color coded it. So here would be sine of theta. It would be this distance here. And then cosine of theta would be this distance here. The a horizontal distance. And what's tangent on this graph? Well, it might not be immediately obvious on this triangle, but what I did here is I drew a line that's tangent to the circle, meaning it intersects only at one point, and that one point is the same place in which the radius of the circle intersects. Since it's a tangent line, we know that this angle here, with that tangent line and the radius as it is going to be intersecting at a right angle. And if this is a right angle, and so I just want to keep in mind, just so you know what I'm looking at this triangle here. This triangle here. This triangle here shares it has a 90-degree angle, and it shares this angle with this triangle. And so this angle here must be equal to this angle here, since the other two angles are equal. And so basically these two triangles are similar triangles. And so if I look at this angle with respect to the big triangle, tangent is going to equal the length of the opposite side over the length of the adjacent side. And looking at this angle, this length right here represents the opposite side. And so we'll just call this O. And so with respect to this triangle, tangent of theta is going to equal O over 1, because this is the adjacent side here. And so that is to say that tangent of theta is equal to opposite O. It's the length of this line segment here. And so knowing all of that, we can label that here. We could say that the length of this side, and we'll do it in another color, the length of the tangent line, and it's interesting because that's probably why they call it tangent, the length of the intersection between the radius and the tangent line and the x-axis here is equal to tangent theta. Okay, so now that we know all of that unit circle, now actually I guess there's one more thing that we should talk about. Everybody should probably know that the area of a triangle is equal to 1/2 base times height. That one's pretty simple. But what about the area of a sector of a circle? And when I say sector of a circle, I'm talking about, for example, this part right here. This little segment here, this pie slice. How would we calculate this area right here? Well, if the total area of a circle is equal to pi r squared, and the total angle here, the total angle is equal to 2 pi, then we could say that the area of this segment here would represent the fraction of theta out of the total angle. So the proportion of theta over the total angle, 2 pi, times the total area of the circle. That would give us this portion of the area of the circle. And the total area of the circle is pi r squared. And so here you'd see that the pi's would cancel, and we get the area of a segment is equal to theta r squared over 2, which in this case, r is equal to 1. The radius of this circle is 1. So in the case of the unit circle, the area of that segment is just going to equal theta over 2. Once again, that's the area of this pie slice here. Alright, so now that we know a little bit about the unit circle anatomy, we can move forward in identifying a few trigonometric limits that tend to come up a lot. The first one is going to be the limit as theta approaches 0 of sine of theta over theta. And you might think, well, you can't just plug in numbers here because you would be dividing by 0, but the limit does exist here because this is a continuous function. And we can actually identify it by looking at this unit circle. So if we compare the areas here of this small triangle here, inside the unit circle right here, this area it's safe to say is going to be less than the area of this segmented area of the unit circle. This little pie slice here represents the area of that plus this additional space here. This additional space here. That's the area of the sector of the unit circle is greater than the area of this small triangle. And it's also safe to say that the area of this large triangle is bigger than the area of those two shapes, because this large triangle contains this space here that is not bound by the other two shapes. So we know that the area of the big triangle is greater than the area of the sector of the unit circle, which is greater than the area of this small triangle. And so let's write out what those actual areas are, and we can color code this. The area of this triangle is going to be equal to base times height divided by 2. Base is cosine of theta, height is sine of theta, so this is just cosine theta sine theta over 2. The area of the segment we determined over here is just equal to theta over 2, so that's going to be greater than this. And the area of this triangle, the big one here, well, the base here is equal to 1, and the height is equal to tangent of theta. So tangent of theta times 1 divided by 2, that's just tangent of theta over 2. Now, I immediately notice that I can multiply all of this by 2. I'll clean things up a little bit. Cosine of theta, sine of theta. It's going to be less than theta. It's going to be less than tangent of theta. And tangent of theta is just sine of theta divided by cosine of theta. Okay. And now what we can do is we could divide all of this by sine of theta. So we get that. That will go away, that will go away. We get cosine of theta is less than theta over sine theta, which is less than 1 over cosine theta. And now I can take the inverse of this whole thing. And when I take the inverse, I have to flip the signs. So you get 1 over cosine of theta. It's going to be greater than sine of theta over theta, which is going to be greater than cosine of theta. And we just proved this geometrically, coming from the areas of these three segments. And so let's ask ourselves, what's the limit of this part as theta approaches 0? What's the limit as theta approaches 0 of 1 over cosine of theta? Well, cosine of theta is the length of this edge here. And if you think about theta being 0, that's going to be, without rotating the radius at all, it's just going to be this point right here. What's the horizontal distance? Well, that's just the radius of the circle, which is just going to be equal to 1. So the limit as theta approaches 0 of 1 over cosine of theta is going to be 1 over 1, which is going to be equal to 1. Well, what about the limit of cosine of theta? Well, we just determined that the limit of cosine of theta as theta approaches 0 is also equal to 1. And so we have a situation where the squeeze theorem is applicable here. Sine of theta over theta is always going to be less than 1 over cosine of theta and greater than cosine of theta. And if the limit as theta approaches 0 of both of these functions, 1 over cosine theta and cosine of theta, is equal to 1, then the limit, by the squeeze theorem, the limit as theta approaches 0 of sine of theta over theta must also equal 1. Another trigonometric limit that we can determine now, that also comes up somewhat frequently in calculus, is cosine of x minus 1 divided by x. The limit of this as x approaches 0. And don't be confused by the change of variables here. Doesn't matter if it's theta or x. It's all the same. It could be theta, it could be x, it could be w, it could be anything. What's the limit of this as x approaches 0? Well, here, of course, there's this x in the denominator, so you can't just plug in values. One thing we can do is we can multiply by the conjugate, cosine of x plus 1. Cosine of x plus 1 If we multiply by this is the same thing as just multiplying by 1, because this divided by this by itself is just 1. And so if we do this, we get cosine squared of x minus 1 divided by x times cosine of x plus 1. And there's something in trigonometry called the Pythagorean identity, which says that cosine squared of x plus sine squared of x is equal to 1. And if that's called the Pythagorean identity for a reason, it uses Pythagorean's theorem. If you look at this triangle here, it's a right triangle, and cosine theta squared plus sine of theta squared must equal the length of the hypotenuse squared, which is just 1. 1 squared is 1. So that's where that comes from. And we can rearrange this. We can rearrange it to get an expression that looks somewhat similar to what we have down there. Here in our numerator right here, we have cosine squared x minus 1. So if we play around with this, we get that cosine squared of x minus 1 is equal to negative sine squared of x. So we can plug that in there. This is equal to negative sine squared of x over x times cosine x plus 1. And now what we could do is we can factor out a sine of x over x. It's equal to sine of x over x times negative sine of x over cosine x plus 1. Now, what's the limit of this as x approaches 0? What's the limit of this as x approaches 0? We know that if you multiply two functions together, that's the same as the limit of this function times the limit of this function. I proved that in my last video, but if you don't care about the proof, you could just watch what happens next. That's the limit of this as this of x approaches 0 times the limit of negative sine of x over cosine x plus 1 as x approaches 0. Here we just determined that this limit was equal to 1. We just determined that right here. And now what's the sine of x? We know that cosine of x as x approaches 0, the limit of cosine of x as x approaches 0 is just cosine of 0, which we showed on the unit circle is just equal to 1. So this is going to equal something over 2. Now there's no problem in the denominator. It's just 1 plus 1, which is 2. What's the limit of negative sine of x as x approaches 0? Well, similarly to how we could just plug in a 0 for cosine of theta, and we got 1, what's the height here? What's the vertical distance from this point? Well, it's equal to 0. And so we have that the limit of cosine of x minus 1 over x is equal to 1 times 0 over 2, which is just 0. So we have just shown that the limit as x approaches 0 of cosine of x minus 1 over x is equal to 0.